everyone. Today we're going to talk about diols. So diols have two alcohol groups. So di stands for two, and then all stands for alcohol. So we have two alcohols. So let's just review some of the reactions we already know that will prepare a diol. So let's say we start with a cis alkene and we add potassium permanganate and sodium hydroxide, and this is run at a cold temperature. Would we add two alcohol groups syn or anti to each other? Syn. So we can just draw those two alcohol groups in wedges. Okay, and then what about if we add osmium tetroxide followed by sodium bisulfite and water? That would also add two alcohol groups syn to each other. And then finally, what if we add MCPBA and sulfuric acid diluted in water? Would that give us syn addition or anti addition? Anti addition. So one of the OH groups will be in a wedge, the other will be in a dash. And you'll notice that when we had syn addition of the OH groups, those resulting molecules had a plane of symmetry, but the one that we drew for anti-addition does not have a plane of symmetry, which means that it can have a non-superimposable mirror image, or an enantiomer. Now, how do we name diols? Let's look at how we can name a diol. So let's just use a simple diol here. So again, the first thing we want to do is count the parent chain, or count the carbons in the parent chain. So here we just have 2 carbons. Now we do have an alkane there, it's a single bond, so we're going to start by naming this ethane to indicate that we have 2 carbons. And then we're just going to add diol to the end to indicate that we have 2 alcohol groups. But we want to indicate where those alcohol groups are located on the 2 carbon chain. So one is located at carbon 1, the other one is at carbon 2, so we'll just add 1, 2 and a dash in front. So this is 1,2-ethane diol. Now there is another way that you could name this. It's more of a common name. So this could also be called ethylene glycol. So just as a note, if you have, for instance, just a single CH2 group in your molecule, that is called a methylene group. Or, as we have above, if you have a 2 carbon group kind of in the middle of your molecule, that's called an ethylene group. And so that's where the ethylene comes from up above, because we have 2 carbons in the center there. An example of where we would use methylene is a pretty common organic solvent, and we've actually used this in lab. This is called methylene chloride. And the methylene is that CH2 group that I highlighted. Or you could call this dichloromethane. So many molecules have multiple names. There's usually an IUPAC name, so the name that's determined by the International Union of Applied Chemistry, or there's a common name that you can use as well. All right, so let's look at another method we could use to prepare a diol. So what if we have the following? So we have a ketone on one side of this molecule and an aldehyde on the other side. How could we turn those into alcohols? So remember in the last lecture we talked about reduction reactions. And what was the reagent we could use with ketones and aldehydes? Sodium borohydride. And in this case, we're going to use excess sodium borohydride to make sure that both carbonyl carbons are reduced. And then we also use an alcohol to protonate the oxygens at the end. So what would the product look like? And feel free to pause the video and try to draw the product. And then when you unpause, we can draw the product together. All right, so at the end, we would have alcohol groups on those carbonyl carbons. And we would have some hydrogens added in as well. So I'll just draw those in there. Now, one thing to notice is that there is a stereocenter on our molecule. Where is the stereocenter? On the left-hand side where the alcohol group is attached. So that carbon there has 4 different groups bonded to it. So we would want to draw that as either a wedge or a dash. And I'm actually going to erase this hydrogen here just to make it a little easier to see. So that means that we could potentially also form the enantiomer. All right, so now let's name this product. How would we name that product? So first we want to find the longest carbon chain. And let's see, we have 1, 2, 3, 4, 5, 6. Okay, so that would be hexane. And then we have 2 alcohols, so that would be diol. And then I numbered going from left to right, but we want our alcohol groups to have the smallest numbers possible. Is there a different way that we could number this chain so that they have the smallest numbers possible? Yes, we can number from right to left. Because the way I have it numbered now, it would be 2,6-hexane diol, but we can actually make our numbers even smaller by numbering from right to left. So now they're at positions 1 and 5, which are smaller. And one other note, because we can form enantiomers here, we would end up with a racemic mixture. So the mixture would be achiral. Okay, so this was a shorter video, but I wanted to just go over diols really quickly. And in the next video, we're going to go over a reaction where we use something called a Grignard reagent. So I will see you then.